described you today, I saw many of you have already submitted, but if you haven't, and please make sure you are making progress. Felipe will have office hours today at 3 to 5 p.m. In E1B11. So you are welcome to ask some questions or email us after that. Okay. All right. So what I basically want to do today is sort of focus more on chapter 11, but just quick recap about where we have been after exam 2. So we have been focusing on boundary layer flows, where we have basically discussed, first we discussed the momentum boundary layer, and there we discussed how we can use scaling analysis, we derive different equations, and we also discussed the Blashes solution. But in essence, essentially, I just want to highlight that you can get these answers to get sort of like a drag coefficient or a wall stress and drag force. In your homework 5 problem 1, you have taken that used the method von Karman's integral method. So hopefully that was also instructive just to see how different methods can give you the same scaling analysis at the end, but with the coefficients being slightly different. And obviously the Blashes solution is the most accurate coefficient there is. Okay. Any questions on momentum boundary layer flows? Anything that has been confusing? All right, let's go further. So this was chapter 9. I just want to make sure that we are clear that this was chapter 9. Now then we start going towards chapter 10, which was forced convection heat and mass transfer. And we discussed this last Wednesday. And that forced convection heat and mass transfer means that the velocity impacts the heat and mass transfer flow. The velocity impacts heat and mass transfer and not the other way around. Okay, so heat and mass transfer do not impact velocity. So there are 2 steps in this problem. One is you calculate a velocity profile, and you calculate a velocity profile based on any of your previous assumptions, like unidirectional flow, nearly unidirectional flow, creeping flows, boundary layer flows, and so on. And then you use that velocity and you input into the heat and mass transport equations. And then that is the way you can calculate the concentration and temperature. So this is essentially homework 5 problem 2 is kind of focusing on this. Okay, is this problem. So homework 5 problem 1 was on the flat plate problem, and homework 5 problem 2 was on this forced convection heat and mass transfer. Okay. So what I really would like to do today is just for 5 minutes, I want to briefly review the grades problem that we did in the class. And I also want to kind of gently remind how it is different than slightly than the problem you're doing in your homework. And then we'll start moving towards chapter 11. Okay, just to kind of refresh your memory about what we were discussing. So what we were discussing was that we have this grids problem where you send something with a temperature T naught in. There's a velocity profile which has been given to us. And then there is a fully developed velocity profile. We have the wall temperature. And then we'll kind of slowly make some sort of boundary layer here. And this was delta T of Z. This was R, and this radius was R. Okay. So remember that when we are trying to write the transport equation, so I just mentioned the transport equation. So velocity profile we knew because that is the velocity profile we knew from earlier. And then we had the equation that Vz del T by del Z is alpha by R. Okay. Alpha by R. Okay. So now here, I want to discuss something that we have not done earlier and sort of like kind of start to make you think about a scaling analysis approach, which is even simpler than what we were discussing before. So you remember we had discussed how we had plugged in some values and tried to calculate the value of this. But remember here the velocity inside boundary layer follows no slip, right? Velocity inside boundary layer follows no slip. And if velocity inside boundary layer follows no slip, a very easy thing to remember is you will use it as u into delta t by r. And I want to be more specific here as it will become clearer as we go along today, is that this is the momentum boundary layer thickness. Can anybody suggest why this is moment? I'm using radius to be the momentum boundary layer thickness. Any thoughts? We are not even talking about momentum boundary layer thickness, but why am I using radius to be the momentum boundary layer thickness? Any thoughts? Any guesses? Like why am I defining it like this, or what is the rationale?
Is it because when it's like fully developed, then your boundary layers the entire like spans the entire radius?
Absolutely, right? Absolutely. So when you have velocity profile in the entire region, the gradients are present throughout the pipe. So the momentum boundary layer thickness is throughout the pipe. So that's radius. Absolutely. So remember this, if your velocity is inside the boundary layer, so I want to be very clear, and follows no slip, then you get this scaling, okay? And then you can just do the simple scaling of what we had before, that delta R is delta T, R goes as roughly capital R because it was close to the wall, and delta Z is Z. If you do all of this, you will be able to find that delta T is equal to delta T cube is equal to U R U R Z U R Z by alpha. Delta T is alpha R by U to the power of 1/3 times Z by R. Delta T by R becomes directly to the power of minus 1/3 C by R 1/3. Okay. So this is what we had discussed earlier as well. So I hope this is clear. Any questions on the scaling analysis? The only difference I have done is I've said because the velocity follows no slip, and because the profile for the velocity is present throughout the pore, I'm just taking sort of like a linear relationship. Okay, so what the idea here is that the velocity will approximate some sort of a linear profile here. So that I want to find at the length scale of delta t, but it goes all the way to u till r. So I'm just taking like a linear ratio of the two boundary thicknesses, and we will do this several times today. So it'll become clearer as we do, but I hope this sort of like the idea is clear. Any questions? All right. Okay. So let's keep going. And then we discussed Nusselt's number, and we said Nusselt's number is equal to 2hr by k. And if you remember that we said h into t wall minus t naught was equal to take k del t by del r at r equal to capital R. And from here, we were able to scale that h would actually be equal to k delta t, rather, let me put it this way, k delta t by delta t being the boundary layer thickness, h here this gets cancelled, or h scales as k by delta t, and finally that means Nusselt's number scales as r by delta t. Okay, Nusselt's number scales as r by delta t. And that means in the developing region, we get Nusselt's number from here. Nusselt's numbers becomes Becquerel to the power 1/3 r by z, 1/3, right? And the developed region developed region, you have Nusselt's number as roughly 1 because our delta T square cells are fully, it has developed throughout. And so if I was to plot the value, versus Z, I will get something like this. It's like a high value at Z equal to small z's, and then it saturates and starts to become some constant value. Okay. All right. So this was just a quick reminder of what you were doing, and for also for your homework 5 problem 2. But any thoughts on what is the physical meaning of Nusselt's number? Does anybody want to kind of what does it mean? What does physical meaning of Nusselt's? If it's high, what should I take of it? Any thoughts?
Could it be the relationship between convective heat transfer and conductive heat transfer? And if it's more of a convective transfer, or if it's a solid, it's going to be conduction. If it's a very fluid, it's going to be convection. So something like that.
Absolutely, absolutely. So basically, this is sort of like a ratio of, and I prefer to use this definition. This is not something I would say very textbook-like, but to me, this has always clarified more. This is total heat by conductive heat. Total heat by conductive heat, and heat transfer, essentially total heat transfer by conductive heat transfer. And this is the way I am defining it. So, but if you all look at this, if you look at this definition of what I'm saying, total heat transfer by conductive heat transfer, the total heat transfer obviously becomes the top, the numerator, which is sort of like this number K del T by del R here, right? So that isn't that weird that I'm just using a conductive expression for total heat transfer? It is the K del T by del R is not conduction, right? So why, how am I incorporating the effect of convection here at all? Isn't just like this a conductive heat transfer all the way? Any thoughts on where the convective part is coming in? This formula is only conductive. So where is the convection part coming in?
We have a H, our convection coefficient now.
Right, but H is also equated to a conductive heat transfer, right, Tim? So it's like H into TW minus T naught is equal to K del T by del R. So right hand side is just a conductive heat transfer. So why am I getting a different number altogether? Any thoughts? And so this is common, and I used to get confused about this a lot. And over years, essentially, you start to see small sort of these details is that remember that the denominator here is delta T. And that delta T is set by the convection. That is set by the, we have seen that the delta T has been set by the convection, right? It is set by convection. So think of it like this. Nusselt's number is telling you a total heat transfer in the presence of velocity, and conductive heat transfer is if there was no flow, what will be the conduction? So if there was no flow, we know the Nusselt's number would just say basically the boundary layer will be thick throughout, right? So will be present throughout. So essentially think of it like this, that even though the heat is being transferred through conduction, kind of similar to the way you were doing this shear stress here, right? We had discussed this. This is still a viscous stress, but the length scale is set by the flow. Similarly, this is a conductive stress, conductive heat transfer, but the length scale is being set by convection. And in the developing region, we see why that becomes, this becomes very sort of high initially, because that's where the boundary layer thickness is comes so small. So essentially, that's where the maximum heat transfer happens. Okay. Does it make sense to everyone? Any questions here? So this is set by convection.
What do you mean by set by convection? I'm still
Yeah.
having a hard time.
I'm trying to say is that look at this, right? If I don't have any velocity, how will I make a boundary layer? Right? So if I have a
Right.
larger velocity, I will make a smaller boundary layer. So that's why like this is so maybe let me try to clarify further. So we also said Peclet number is UR by alpha, and that is greater than 1. I hope you will all agree that Peclet number is also the ratio of convection by conduction, right? In a way. But that is a very approximate number that for that you don't need to calculate anything. You just need a velocity, radius, and alpha. But here you kind of start to think more microscopically. So look at that Nusselt's number does not go as Peclet, is not proportional to Peclet number. It is proportional to Peclet number raised to the power of 1 by 3. So Peclet number is an approximate way to say convection to conduction. But Nusselt's number is really the true total heat transfer by conductive heat transfer. I just want to kind of clarify. So like if you want to think about which terms to drop, you can use this Peclet number. But then when you want to really think about how much heat transfer is occurring, then you have to go towards Nusselt's number. And the point being that sometimes it can be confusing that, oh, well, if I'm just taking a K del T by del R, it is purely conductive. Then how do I even have a convection? That convection is hidden in your boundary layer thickness. Make sense?
Yeah, a little bit. Thanks.
Any other questions here? Any confusion? Okay, so we will do this a couple more times. Hopefully, this will become clearer by the end of the lecture. And this is an important concept. Like I think if you can understand scaling analysis, you really have understood the process very well. So I want to emphasize in the last chapter 10 and 11 the importance of scaling analysis. Okay, so let's do another few minutes of like the problem that you're doing in your class, in your homework about the falling film diffusion in, right? And here I have some sort of falling film here with some velocity. You calculate it first, right? And then some C naught was going in from here. So initially this was solute free. So nothing was being dissolved here. Just to clarify, we're talking about this falling film like this here. And then you have like the solute enters through the film. Now, you all found the velocity profile. You will have found the velocity profile. And then the point being, I just want to do the scaling analysis. So the velocity is Vx del C by del X. So this is kind of like the scaling analysis I have. Right? Any questions on this? Just a governing equation. I hope this is clear. This is what you are doing in your homework. Right? So, and you can ignore the del square C by del X square because that length scale is much larger. So it really becomes down to del square C, convection being balanced by diffusion. Convection in the X direction being balanced by diffusion in the Y direction. Now, the first question I have for everyone is, where is my boundary layer forming? This is H. This is Y equal to 0. This is Y equal to H. Is my boundary layer forming in Y equal to 0 or at Y equal to H? Any thoughts?
It's forming from H, yeah.
So that's a very common sort of oversight. Is this is actually forming like this, right? Because it's entering through the fluid phase. Remember that it's not entering through the solid phase. The solute is entering through the gas phase. So this is very common confusion because we see the velocity to be no slip from the wall, but note that this is actually a boundary layer from this side. Does everybody see that point? So maybe let's give another color. Hopefully that will be better. Let's see some red color. Okay. This is basically my part of the. Does it make sense, Jason? I think it was Jason who answered. This was. It's
Yeah,
from,
yeah. I was
Yeah,
thinking of that fluid flow.
right. So it's from the mass transfer boundary layer is occurring through the y equal to 0 side. And why is that important? In the boundary layer, is there any no slip right now? No, right? There is no slip because it's just at the fluid interface, liquid air interface. So my Vx will simply be u. I do not need to worry about any no slip or linearly scaling like I did here at the fluid solid interface. I can simply do Vx is u. That's it. And you just do delta x is x, delta c is c naught, delta y is delta c. And if you plug all of this in, you will get delta c is, I believe it comes out to be dx by u raised power of half. So you will get it to be u h by d into x by h raised power of half. Or the Sherwood number here, which you're calculating, will be h by delta c is, and this is Peclet number. So it will become Peclet number to the power of half. So it's actually, let's just write it down. Becomes Peclet to the power of minus half, x by h to the power of half, or Sherwood number is okay. Any questions here? Does this make sense? Does it make sense? Any questions here? So the difference really is that there is no slip in the boundary layer, in the concentration boundary layer. So no slip. Concentration boundary layer. Okay. Any questions here? I hope you can see the difference between this. And so when you do this problem using similarity in your homework, you will be able to kind of appreciate sort of the difference with, with the other one, with the grades problem, where we get a 1/3 scaling, but here we are getting a 1/2 scaling. All right. All good?
One question.
Sure.
The fact that we're getting 1/2 in this problem, is it because the boundary layer is like fluid, or what's the reasoning?
Yeah, so the main point is that the no slip is not satisfied, right? So I mean so why do you get a 1/3 scaling out there is because your velocity here has this dependence here with delta t. So when you do that, when you kind of comparing the two, so there is a delta t on the left hand side as well as the delta t square from here on the right hand side. But when you don't have this to be independent of delta c, then you simply get a delta c square from here. Make sense, Julia?
Yeah. Okay. Thank you.
So the scaling, basically the point is that a 1/3 scaling sort of signifies that your boundary layer thickness, the velocity inside the boundary layer thickness is itself dependent on delta t or delta c, but that's not the case. So that's why. Okay. All right, I just want to make one more point, and then before going further, is that if I was to not start having some sort of solute coming from here, right, then you can imagine this will become a 1/3 scaling because no slip will start to be important. Okay. So it's because on the fluid side, if there is if I kind of make a new problem and have some solute coming from that side, then that will basically be what can happen. And you can imagine I can have one solute going from the fluid air interface and one solute coming from the solute water interface, liquid solid interface. So the two boundary layers will be very different. On the solid side, we have 1/3 scaling. On the fluid side, you will have the 1/2 scaling. All right. Any more questions here? All right. So just want to clarify one point that we have been discussing. So chapter 10, what we have really discussed is Peclet number to be large and fluid is fully developed. Fluid flow is fully developed. So this is the only case scenario we discussed. Now we go to chapter 11, which is the now we go to chapter 11, which is force, convection, heat, and mass transfer out around objects. Okay. Unconfined flows. So force, convection, heat, and mass transfer. Or in unconfined flow. Okay. Unconfined flows. All right. So physically, what do you think is the downside of unconfined flows? Like, or sort of like confined flows are nice in a way that you only have one velocity. But now when you start to think of unconfined flows, flows around a sphere, flows around a cylinder, you can imagine that now we'll start to have bidirectional flows. We'll have multiple directions coming in, complicating our analysis. Okay. So that's why unconfined flows are generally taught later. All right, just let's take a quick poll here just to kind of hopefully to keep everyone engaged here. Let's do that. What do you think is the, what do you think is the application of unconfined flows? And this is these kinds of questions are more for just so that you can see all the applications. So I'm sure all of you can see. So we are really thinking about that all of these applications will have the flow around in unconfined flows, because in heat exchanger there's an inner pipe and then there's an outer pipe. When the flow in outer pipe is flow around the outside the inner pipe, so there is sort of like heat exchanger design. In cooling fin design, also you have, when you have fins coming out, we had discussed fins in part 1 of the course. You add a fin to increase surface area to heat cool something, but the flow is around these fins, and so it's again mass separation, so stripping, absorption, leaching. You always have something flowing around, some sort of a fitting, or you have some sort of a surface area, like a really large surface area. And then biomaterials, drug delivery, again you will have some sort of like so in biomaterials, so for instance you can imagine some sort of a tissue, and if you have to think of something like flowing around tissue or something like that. So it is really like pretty kind of like wide application of unconfined flows. And I have had students who have come up to me in their PhD research at Boulder and who are actually using some of these things about unconfined flows in their research. So it's a good topic, and we will not do much of math here. We'll mostly do scaling analysis, again with an intention that you will be able to understand what's going on in detail. Okay. Any questions here before I go carry on? All right, perfect. So let's carry on. So what we will do now is we'll start to think of flow around a sphere. So unconfined flow. So flow around a sphere will be our model problem. This is kind of like a toy problem where it will give us insights into what goes on in things. So we have some sort of a sphere here of radius r. Let's imagine this is at some temperature T wall. Some fluid is flowing over it, which has a temperature far away, it has a temperature T naught and velocity U. Okay. So you can think of a heated ball essentially. You have a heated ball lying around and flow is coming throughout it. The air flow is T naught. So if the ball is hot, it will heat up the air. If the ball is cold, it will cool the air. So basically, it can have that kind of heat transfer. It can also be something dissolving. So not really dissolving, kind of sort of solute is sort of being dissolved, but the ball being like some sort of a mass of solute, that can also happen. So, but we are thinking of heat transfer just as, because the equations are analogous. Okay, so here remember that fluid flow is not like a unidirectional pipe flow, right? It can have different like it can have different formulas. So we have two steps here now. One is to solve the fluid flow, and one is to solve the heat transfer. And at the end of the day, all we will be doing is trying to calculate the scaling analysis for Nusselt's number, like we were doing for Sherwood number, which is basically Nusselt's number in solute transport. And Nusselt's number here, all we want to do is to understand different scaling analysis for Nusselt's number here. Okay, so let's start the process. So how will we think about this? So governing equation. For simplicity, let's not worry about gravity and this right now, like the unsteady part. We'll just say, so steady. So we'll assume steady and ignore gravity. These are our governing equation. And our equation will become alpha del square T. Okay, so this is essentially our equation for heat transfer, because I would ignore the time dependence part and we are not generating any heat anywhere. And remember that we are solving this problem. Okay. In this region, right? All right.
I have a
So
question.
Yes, please go ahead.
Are we also ignoring the pressure?
No, so pressure is
Or
here.
where is it?
Pressure is here, right? Minus grad P.
Okay. No, it's just in the final equation you put down.
Oh, this is the heat transfer equation.
Oh,
So
right. Sorry. Yes.
any other questions? All right. So basically, we have, I want you to kind of remember that we have two dimensionless groups, Reynolds number and Peclet number.
Unclear.
Yes, go ahead.
Should it be then v dot grad of t?
Oh, sorry. Thanks. Probably that was the confusion. Thanks, Julia. Yes. Absolutely. Thanks, Julia. Also, this is v dot grad t. A mistake. Heat transfer. Any other questions? All right, perfect. So basically, now we have two dimensionless numbers. This is u r by nu, and this is u r by alpha. I believe the book uses 2 u r by alpha. I mean, you can use u r by alpha, 2 u r by alpha. It doesn't really matter. But let's just use 2 u r. I think believe the book does 2 u r. And we'll find the Nusselt's number as 2 h r by k. And if you're wondering why they are using 2 u r, it's because they are using diameter instead of radius. That's really it, nothing else. And we want to find 2 h r by k, and this is the whole point. So the whole idea here is to sort of find different limits. Okay, so let's find different limits, and I want to discuss the different limits. So you have Reynolds number less than 1, and Peclet number less than 1. We'll have Reynolds number less than 1, and then Peclet number greater than 1. Then we'll have Reynolds number greater than 1, and Peclet number greater than 1. But this limit will have two parts: Prandtl number greater than 1, less than 1, and Prandtl number greater than 1. Okay. So these are the limits we want to discuss. So there are 4 limits: 1, 2, 3, and 4. So I first want to clarify. Okay, these are the 4 limits you want to discuss: Reynolds number small, Peclet number small, Reynolds number small, Peclet number big, and both Reynolds number and Peclet number are large, but Prandtl number is smaller, Prandtl number is big. And it will become clearer why Prandtl number comes in. I'll explain that as we go along. But any questions about different limits, or if you if there is any confusion, I'm happy to. Yeah, there is always a limit that sometimes students might think, oh, well, can I have Reynolds number to be large and Peclet number to be small? That is very, very unlikely. But that's because of the physical properties. So that's why the limit, that's the only limit we don't discuss, is when Reynolds number is large but Peclet number is small. That is very unlikely to happen because momentum diffusivity is much larger than the thermal diffusivity. So that's why that limit is not really that crucial. So we'll not discuss this. Any other question? Any questions here? Anything to discuss first before I go on? All right. Okay. Perfect. So, what do you think? What do you think is this limit? What should I expect in this limit? If Reynolds number is small, Peclet number is small, what should I expect? Which heat transfer do you think will dominate, and how can I solve this problem?
Should be mostly diffusion, yeah.
So Jason says it's mostly diffusion. If it was not already clear, I should just mention the boundary conditions for temperature here. The boundary conditions for temperature are we have been given these boundary conditions because that's the main two boundaries. Okay, perfect. So Jason said conduction dominates, and let's do a quick poll here to see which one do you think for small pattern, and Reynolds number is small by the way already. So if for this question, which, and I've just written in the vector form the equation that you saw earlier, so the scalar form from the instead of the vector form, which do you think is the I should be able to find, hopefully, yes. We should be able to see the whole now, and which terms do you think we can simplify? So with an idea thinking that, okay, we can ignore the convection. So maybe take a few more 15 seconds more to kind of think about it. All right, maybe one more. All right, let's end the poll. So basically the maximum response is for C, followed by E, which is keep only radial conduction, and the answer is actually E, that you only keep radial conduction. And this is one of the most common confusions that I've seen about this problem is So most of you did get it right. So I hope first it's clear that it will be mostly so if Peclet number is small, you can ignore convection. So it will become del square T by equal to 0. Now the question really is, why should I remove why not have the theta dependence? Okay, so if anybody wants to volunteer of why they picked, they did not pick theta dependence. Does anybody want to share why they thought there should be no theta dependence?
My logic was sort of like, if the velocity is so, if the Reynolds number is very low, then the velocity moving around the sphere is very low. So that's kind of what drives sort of the advective theta transport, right?
Right. So you're going in the right direction. So I want to follow up on this comment. So this is the term that so I hope you can all see this sort of highlighted term. So this term is purely conductive, but still depends on theta. So I think that's where Jason was going. That this is correct. So think of it like this: Reynolds number small and Peclet number small basically means that convection doesn't matter. So that's clear. So we can ignore these two dependencies. So the left hand goes away. But on the right hand side, we still have two terms. And then why should I ignore the theta dependence? The point is that there is no reason for it to have a theta dependence. If in my setup, I don't have flow. So think if I don't have flow, there is a fluid chilling out far away with temperature T naught. There is no flow. Then why, and that the sphere is homogeneous, then why should I have a theta dependence? So there was a question last time, what if I have a fluid, if I have a sphere which is half T wall and half some other temperature? In that case, you have to keep a theta dependence, because then there is a I have added a theta asymmetry. But in this problem, because it's a homogeneous sphere and homogeneous far field, we should not expect any theta dependence. So it's sort of like almost like a simplification by sort of intuition. A mathematical simplification, if you're not satisfied by this, is the fact that boundary conditions are not dependent on theta. So if I have any asymmetry in the boundary condition of theta, then I can expect a del by del theta in the conduction, but the boundary conditions are also not a function of theta. Okay, so that's why you ignore this and you can just solve this. Make sense? Any questions here? So no theta dependence. So no theta dependence. Ignore due to symmetry. All right. So then finally you can solve this. I'll encourage you to, because we discussed all of these things in a first part of the class, but you can solve this actually. It comes out to be T naught. So you can solve this problem and you can calculate H into T wall minus T naught is equal to minus K del T by del R equal to R. And you can use this to calculate 2HR by K. And this becomes, comes out to be 2. Nusselt numbers comes out to be 2. Okay. It's not that important, but like I just think if like you're getting kind of, if you want to do like a more mathematical practice, you can solve it. It's just takes 10 minutes to do it, and you will be able to find that Nusselt's number is actually equal to 2. Okay. So this simple Reynolds number is small, Peclet number is small. We knew that conduction will dominate, and Nusselt's number is really total heat transfer by conductive heat transfer. So simply 2. Okay, that's simple. Another way to think about from a scaling perspective is that Nusselt's number is radial dependence by delta T, and there is no other length scale here other than R. So I should expect Nusselt's number to be on the order of 1, right? So that is another way to look at. You can do the mathematical route, or you can just think of it like this, and then you'll be also able to come to that point. Any questions here? Anything that's confusing? Please feel free to ask. Don't hesitate if there is any question. All good. Okay. So now let's look at the second limit, which is Reynolds number less and Peclet number large. So in this problem, what do you think? What should I do in the Peclet number? If my Peclet number is large, what should I do to my governing equation V dot del T? Should I ignore the right hand side completely, or what do you think is going to happen? Any thoughts? Anybody? So you have fluid flowing and then speed is very fast. Anybody wants to guess? Should I just ignore the right hand side?
Maybe not completely, but yes, in one direction.
So why do you think we should not ignore it why shouldn't we ignore it completely? Any physical intuition? That's fine. I mean, why shouldn't I ignore it completely?
Well, heat has to come from somewhere, and if we're just pulling it along by convection, then you're not heating it up at all from the ball.
Absolutely, right. So in other words, if I remove one derivative, then I will not be able to satisfy my boundary conditions, right? So again, this now, whenever you start to see that you're ignoring a second derivative term, that means it should click, there's a boundary layer, right? When I have a large Peclet number, so see how it disconnects your flow and confined flow. There also was Peclet number large. When there is a large Peclet number, there is a boundary layer, because if I ignore the conduction completely, then I have dropped a derivative, or I've dropped the sort of boundary condition. Or physically, like Colin put it, that if I'm just transporting something by convection, I have to balance it with something, and that balance has to be come from the boundary layer. So there will be a thermal boundary layer delta T. Okay. So earlier I used to actually go through the full exercise and show some more details here, but I think I felt like it was a little bit confusing to students. So there is a supplementary video which discusses and goes into more details here about some of the scaling relationships in velocity. So I encourage you to go through it, because it is insightful. I just think it can be sometimes confusing in case because many things are going on. Remember, Reynolds number is small, so it's a creeping flow problem. And if it's a creeping flow problem, you know the velocity. You have calculated velocity of flow around a sphere, so you actually know the velocity profile, and you can go through the steps to calculate some of the things. But in the interest of sort of simplicity, I will just sort of remove that. But there is a supplementary video if you're interested and are keen to learn more about the details. But think of it like this: whenever we have a boundary layer, we remember that we define y and x, which is what we'll do here as well. Y and x, and then we'll have a delta t. Okay, delta t. And instead of writing all of this down, I want you to remember this. All you can say is Vx. You can show this more rigorously. I just find it to be easier to just write it like this. Vx del t by del x is alpha del square t by del y square. Physically, it makes sense, right? So this is where what Colin was saying is that convection has to go somewhere, and that's going to diffusion in the normal direction, or conduction in the normal direction, right? So you can just simplify for order of magnitude analysis. This is not an exact formula, by the way. This is not exact. There will be other terms here, but I'm just saying for a scaling analysis perspective, this is all right. Okay. Any questions here? And now I will start to ask, we'll do a lot of scaling analysis here now. So first, any questions here? So why we are zooming in and we are saying that this is what's going on. And note that in confined flows, we did local predictions like X, Z. But here we'll just scale everything as radius. Okay. We are trying to find an average Nusselt number. We're not trying to find a local Nusselt number. So we'll not do like any dependence on X or theta or R or theta or Y or anything, just a average Nusselt number. So what do you think is our delta X? Anybody wants to guess? Any ideas? You are going along a sphere, so it should be scaled by radius, right? Basically, the kind of like a path line, but some sort of proportionality constant to the radius. What should be delta Y?
Delta T.
Delta T, good, delta T. And delta T should be T wall minus T naught, right? And now the most important question, what do you think should be Vx? How should I think of Vx? Anybody wants to guess? So remember the formula we have discussed. Velocity will scale as it will scale as a first we have to satisfy velocity inside the boundary layer. So we are thinking of velocity inside the boundary layer, right? This is the boundary layer. And it follows no slip. Yes, it follows no slip because it's a solid surface. By the way, this is a solid, I think we have discussed, but this is a solid heated surface. The solid, right? So what is my momentum boundary thickness in this problem? So I say U delta T. What should I divide here by? Any thoughts? So if we have a creeping flow outside, Reynolds number is small, what is the length scale at which the velocities will decay? Any ideas, thoughts? No guesses?
Would it
What?
also be R, the radius?
Yeah, right. There is no momentum boundary, like there is no like it's a creeping flow. So there is no other length scale that can come in. It has to be only radius. So remember that when you used to do your tau and you did some of this in your class as well, in your homework as well, you get a mu u by r, right? Mu u by r is radius because this is the boundary layer thickness. So essentially you get is a u delta t by r. Yeah. Okay. Because that is the only thickness, because the velocity will be 0 here and then it will be decay on the length scale of r, but I am very close to the surface because for heat transfer, that is the region I am interested in. So it will be u delta t by r. Okay. Now, what if there was a bubble? Would I be able to do this instead of a solid? Somehow add a cold bubble or a hot bubble. Will I be able to do this?
No, because you don't have no slip, right?
Right. If you don't have no slip, it will just be u. Velocity slips u. We don't have to worry about like the scaling. It will just be simply u. Okay. So you do this. And so let's do this. We'll get u delta t by r times t wall minus t naught by r, another r here, then alpha t wall minus t naught, and then delta t cube. This cancels out. You get delta t cube is alpha r square by u, or delta t by r becomes alpha by u r to the power of 1/3. It becomes spectral to the power minus 1/3. Or finally, Nusselt's numbers becomes And you may remember this is something you may have written in your undergrads, that Nusselt's number goes as Peclet to the 1/3. And might have been taught to you, but you can see there is a rigorous derivation behind it. You can actually also calculate it fully. Book has a full solution. And this is a very important result because flow around a sphere, heated sphere, has been very important for chemical engineering. So Peclet number to the 1/3 you can calculate. And why 1/3 again? Remember, this scaling is 1/3. 1/3 comes because there is a no slip, and that there is a no slip, and then there is a thermal boundary next to it. Okay. Any questions? All good. All right. So now let's go to the final case, which is when we have the Reynolds number greater than 1, Peclet number greater than 1. All right. So Reynolds number greater than 1. So third and fourth case, Reynolds number greater than 1, Peclet number greater than 1. So what do you think will happen now? So now I have creeping flow goes out of the window, but I also have now I'll have flow fast, and then I will have heat also. So what do you think will happen? Just in words. If I have both numbers to be large.
No diffusion.
So I think you're going in the right direction, but remember that if I remove diffusion, then I will not be able to satisfy my boundary conditions. Same for Reynolds number. If I remove momentum convection, then I will get the same problem that there is no drag and so on. So what happens is there are both boundary layers. So now I have a thermal boundary layer and I have a momentum boundary layer. So I get now a delta T and a delta M. Okay. So I have both boundary layers. Okay. So convection is dominating in both cases, but I cannot remove diffusion because otherwise I will not be able to satisfy no slip and a heated surface. And so I have both boundary layers. And so let's do a quick question here to think about what do you think will typically happen in these boundary layers. So you can also have a concentration, by the way, concentration problem. For a typical liquid, what do you think is the should the momentum be thickest, concentration be thickest, or let's do that now. So there are three boundary layers which we were discussing can happen over sphere. I've just gone again zoomed in to X and Y. Which one do you think will be the smallest, and which one do you think will be the largest? And as a hint, think about the momentum diffusivity, thermal diffusivity, and mass diffusivity, species diffusivity. All right. Maybe a couple more students are left. Okay. So everybody has participated. So it's a pretty split result from between A, B, and C, almost 1/3 each. So I'll end the poll. The correct answer is actually B, where the concentration is the thinnest, then it's the thermal, and then it's the momentum. And why is that? Like, am I just making this out of anywhere? The point being that, so if you have these three, this will be delta C, This will be delta. That's because the Prandtl number, remember we had discussed that mu is greater than alpha is greater than d. Okay, so remember that momentum boundary layer was proportional to nu raised to the power of half or something. And then boundary layers thickness is like this here, delta t are proportional to alpha, right? Like some exponent, but increasing alpha, increasing delta t. So similarly, same for concentration. So then nu is greater than alpha greater than d. So typically this happens. However, you can have other cases. You can find some new material, or you may have discovered something that is a new material. And there's some very few cases where you do see a reversal, but a typical liquid will always have this. Okay. So a typical liquid will have the thinnest one to be concentration, then thermal, then momentum. Okay.
Is the length of the boundary layers related to how fast the profile develops or
You
not?
yes, absolutely. So the thickness of the boundary layer does depend on velocity always. But relatively, the three of them will always have this. But yes, the thickness of all of them will change. If you have a velocity changing, then the thicknesses will change. Yes, like I mean, we see here, right? That whenever you have the velocity to be large, the thickness decreases. That will happen for all of them.
Right, but does that mean that the velocity profile will take longer to develop than the concentration profile, or is that not okay?
Absolutely. So that's a great question, Julia. This excellent question. So it's absolutely true that. So what Julia is saying is, well, if I'm looking at the concentration boundary layer, my velocity hasn't really developed fully because it's really developing until delta m, and that's absolutely true. And that actually does change the scaling, as we will see just in a minute. Okay. So let's now think we are Reynolds number one greater than one and Peckley number greater than one.
So sorry, one more question. Where does this inequality, this new bigger than alpha, bigger than d come from? I'm not trying to understand.
Oh, so this is just something, a physical property of a liquid. So this is not something we have discussed like, this was, we discussed in part one, like not as a derivation, but a liquid, I mean, you can measure these things, right? This, like a thermal diffusivity, momentum diffusivity, and species diffusivity. So remember Prandtl number, Schmidt number, sorry, Prandtl number and Lewis number. Lewis, and there was another one, Schmidt number. These three we had discussed back, and so these are just typical liquid properties. This is not something that we have derived essentially. So people have measured it, and it turns out that momentum diffusivity is much larger than alpha, much larger than d for liquids. For gases, they're all same, which makes it a mess to solve a gas flow. That's why. Make sense, Tim?
Yes, so it's just sort of empirically true. It's not something we derive.
Correct. Yeah, empirical values. These are empirical values. Yeah. I'm
Okay,
sure there might be some physical basis behind them, like some sort of a molecular theory of liquids, but I'm not familiar with that literature. Yeah. There might be ways to explain it. I just don't know how to do it. All right. Any other questions here? Okay, so for typical liquid, basically, we know that nu is by alpha, which is called Prandtl number, is greater than 1. So that's what we'll discuss first. Okay, so let's imagine Reynolds number is greater than 1, Prandtl number is greater than 1, and Peckley is greater than 1, and Prandtl number is greater than 1. So if we have this system, then I'll have two boundary layers. I'll have this to be delta T, and this to be delta M. And we'll have Vx del T by del X as alpha del square T by del Y square. Okay. Vx del T by del X is similar to alpha del square T by del Y square. We have discussed this. This is something you should remember. Convective balance can be written like this. Then X delta X will be similar to R. We remember we are still in a sphere. Okay, this is just zooming in. Delta Y would be delta T, right? Because I'm interested in the thermal boundary layer. Temperature differences only. Okay, I'm not thinking about the momentum boundary layer right now. Delta T will be T wall minus T naught. And what do you think will be Vx? Anybody wants to suggest? What do you think will happen to Vx?
Is it still scaled by the momentum boundary layer?
Yes, absolutely. So this is U delta T by delta M. Right now, it's not radius R. So for a creeping flow, that length scale was radius, but now it is not radius, it is delta M. And do we know how delta M scales? We know it scales by U delta T by Reynolds number R times Reynolds number to the power of minus half. Right? We had discussed this, that it's the delta, you remember the delta by L goes as Reynolds number to the power of minus half. That's what I'm recalling here, because noting that length here is the radius of the sphere. Okay. Any questions here? This is, we substitute this back, and then we'll say U delta T by radius Reynolds number to the power of minus half is similar to alpha, sorry, not delta T, this one, capital delta T. Wait, there was a delta T. The delta T here, and then capital delta T, this goes away. Then I get delta T cube is equal to alpha R by U times Reynolds number to the power of minus half. I feel I'm making a mistake somewhere.
Should it be R squared in the denominator of the left-hand side?
Yes,
The
yes,
derivative?
because there is another derivative. Yes, thank you. Yeah, that's why I was thinking I'm making a mistake somewhere.
Coming from the delta X, right?
Correct. It's absolutely right, Jason. Right. And then there is an R square, so there is an alpha R square here. So this is the velocity, this part and this part. And then the R remaining is the delta X part. So that's why my dimensions are coming out to be wrong. And so delta by R becomes UR by alpha, 1/3, Reynolds number to the power of minus 1/3, sorry, minus 1/6. Or delta T by R becomes Peclet to the power minus 1/3, Reynolds number to the power minus 1/6. Generally, this is not, you can leave it in this form. That's absolutely fine. There is nothing wrong here. But generally, people prefer to kind of expand this Peclet number as Reynolds number times Prandtl number. And you can verify, this is very easy to verify. So delta T by R becomes Reynolds number to the power of minus half, Prandtl to the power of minus 1/3, or Nusselt's number becomes. All right, so this is a little bit more complicated because we have now the momentum boundary layer also becoming a function of Reynolds number. So which is because they're both larger than 1, and that's why this becomes more complicated. Okay. Any questions here? Right. All good. All right, so let's keep going. We only have 5 more minutes. I just want to make sure I get there. Finish. There's only one last analysis left, and so we'll then close out the lecture and this chapter as well. So finally, we have Reynolds number greater than 1, Prandtl number greater than 1, but sorry, Peclet number greater than 1, but Prandtl number is less than 1. That means I will have the opposite now, that I will have the momentum boundary layer like this, and this is delta T. This is a very uncommon scenario, but let's just discuss this hypothetically because it's instructive. So we will have Vx del T by del X del square t by del y square. Everything remains the same. Delta t is t ball minus t naught. Delta x is r. Delta y is delta t. So the only basic thing is what is Vx. All right. So this is the question. What do you think is the velocity scale? So does anybody want to suggest what do you think it will be? So can I use the one what I was using always? So saying that this is u delta t by delta m. Should I use this? I mean, I've been using this all along. Anybody wants to guess yes or no? So, okay, maybe let me rephrase the question. Is this velocity greater than u or less than u? U delta t by delta m.
It's greater than u, yeah.
Greater than u, right? Because we are saying that the thermal boundary layer thickness is much bigger than the momentum boundary layer thickness. And can the velocity be greater than u?
No.
No, right? So that means, and we can physically understand this because this was what Julie had mentioned long back, is that now it develops so fast that in my thermal boundary layer, I actually only experience u. I don't experience that the no slip because thermal boundary layer is much thicker. So it simply becomes u. Okay, we cannot have it larger. You can use that formula if you would like, but that is a little wrong because then you're saying it's larger than u, which is not possible. So you scale this as u, and I will let you do this, and it's very simple to get this, but you will get delta t to be by r to be u r by alpha to the power of half, or Peclet to the power of minus half, and that means Nusselt becomes Peclet to the power of half. Okay. So essentially, we have discussed till now 4 cases today. So if Reynolds number is less than 1, Peclet number is less than 1, we get Nusselt's number of 2. If Reynolds number is less than 1, Peclet number is greater than 1, we get this to be Peclet to the power 1/3. If Reynolds number is less than 1, Peclet number is greater than 1. Then we have 2 cases. Prandtl number is small or Prandtl number is big. Prandtl number is the usual one, which becomes Reynolds to the power of half, Prandtl to the 1/3, and here you get Nusselt to Prandtl to the power of half. Okay. Any questions on the scaling analysis? All right. So before I close out the lecture, I just want to show you one thing quickly. Just give me 1 second. So this is really the chapter 11. We are done with the chapter 11. I'll just take 1 minute to show you. In the book, actually, there is a table just so that you can keep it in your reference for your exams and stuff, and just for your knowledge as well. So 1 more second, just going to the right page. All right, so just let me push it here, and then we'll close out the lecture. As you can see here, we get the if and by the way, all of this, if it's fluid, then everything just becomes Peclet number, right? So remember, Reynolds number times Prandtl is Peclet. So all of this essentially here is just trying to tell you whatever the cases we had discussed. The only difference is they have written in terms of Reynolds number times Prandtl number. So let's say the last part is Reynolds number times Prandtl number to the power half. So these are all like, but we have discussed these cases. So just wanted to mention the table 11-2. You can use this, in your any exams or anything like that. All right. So that's all for today. Thank you for joining over Zoom, and we'll post the lectures. And if you have any questions for the exam, for the homework, please feel free to drop by Felipe's office as today. I will have to rush to another meeting. But if you have any questions for me, don't hesitate to email me, and we can set up a time to meet, or I can answer over email. All right. Thanks a lot, everyone, and have a good rest of the day and stay warm. All right.
Thank you. I have a question, Ankur, before you go. Are we gonna have a last homework?